This is part 2 of the detailed tutorial on simulating a 3-degree of freedom robot manipulator using Simscape Multibody and Matlab Simulink. If you haven't watched part 1 yet, please go back and watch the first video. Now, we move on to implementing coordinate frame 3. Following the Denavit-Hartenberg convention for assigning coordinate frames to the robot, we observe that coordinate frame 3 is translated from frame 2 by a distance of L2 along the positive Z2 axis. Therefore, we will use a rigid transform block to execute this translation by L2 along the positive Z2 axis, thereby transforming frame 2 into frame 3. The detailed setup for the rigid transform block is shown in the image on this slide. To implement the transformation based on the analysis above, we take out the rigid transform block. The detailed configuration settings for the rigid transform block are performed as shown in the video. We select Cartesian for the translation method. Under the offset parameter, we input 0.2 meters into the third element of the vector, which corresponds to the z-axis. Joint 3 is a Revolute joint. Therefore, we will copy joint 1 to create joint 3. We then connect joint 3 immediately after the transformation block. At this point, we select the components of link 2 and create a subsystem by right-clicking and choosing Create Subsystem from selection. Inside the link 2 subsystem, we rename the connector ports. The link 2 subsystem block consists of one port connecting to joint 2 and another port connecting to joint 3. To represent the Revolute joint 3, we utilize a cylindrical solid block. We then configure the parameters for its dimensions and color. For the detailed steps, please follow along with the video. We connect the newly created cylindrical solid block to joint 3 and then run the simulation to observe the results. The final mechanical component in the construction of the robot manipulator is link 3. We will take out the brick solid block and set up the parameters for its color and dimensions. The length of link 3 along the z-axis is equal to dimension L3, which is 0.1 meters. Next, we navigate to the Frames section and select New Frame to create the connector ports F1 and F2 for the link 3 block. Following this, we run the simulation to observe the results. We now select the components of link 3 and create a subsystem by right-clicking and choosing Create Subsystem from selection. Inside this subsystem, we will rename the connector ports. The link 3 subsystem block consists of one port connecting to joint 3 and the other port serving as the robot's end effector. In order to obtain measurement data for the motion of the end effector, we take out and use the transform sensor block. We will rename the block to end effector sensor and connect it to the end effector port on link 3. In the measurement frame setting, we change the reference frame to base. This ensures that the motions are measured in coordinate frame E relative to coordinate frame 0. For port B of the sensor block, we copy the blocks previously created to implement the transformation from the world frame into coordinate frame 0. The output measurement signals for X, Y, and Z are physical signals, PS, within Multibody. Therefore, we need to use PS to Simulink converter blocks to convert them into standard numerical signals. We now access the Simulink library browser and take out display blocks to show the resulting X, Y, and Z coordinates of the end effector as measured by the sensor. Now, we configure the settings to provide input signals for actuating the robot's 3 joints. We will set this up within the actuation parameters of the joint blocks. Under the motion setting, we select provided by input. We also select position under the sensing parameter to get the joint motion measurement output. The input information consists of the desired values for the rotation angle of joint 1 and joint 3, and the translation distance of joint 2. We must use the Simulink to PS converter block to change the numerical signals into physical signals. For detailed implementation steps for each joint, please follow along with the video. The desired input signal for joint motion comprises the desired angle, velocity, and acceleration. The desired rotation angle for joint 1 is defined by the variable name θ1d. The velocity is set to 10 and the acceleration is set to 0. For the joint's measurement output signal, we also need to utilize a PS to Simulink converter block. Similar to joint 1, we now perform the work of setting up the input and output signals for joint 2. Next, We proceed to set up the input and output signals for joint 3. We now connect the X, Y, and Z output signals from the sensor to the output blocks. These represent the position measurement results of the end effector in the Cartesian coordinate system. At this point, the mechanical modeling of the robot manipulator's components is complete. We run the simulation one last time to verify and ensure the robot model is fully finalized. After verification, we select the entire model and create a subsystem. We name this subsystem, Robot Mechanical Model in Multibody. Next, we take out the constant blocks to generate the desired input signals for the robot's joints. We will also use display blocks to connect to the outputs of the robot model. We now arbitrarily set the desired input signal values for the robot joints for testing. Here, we set the rotation angle θ1d to pi/3, d2d to 0.1 meters, and θ3d to pi/6. Then, we run the simulation to observe the results. The robot has moved according to the desired set point values. To compare and verify the results with calculations derived from the forward kinematics equations, we go to the library and take out a MATLAB function block from the user-defined functions category. We double-click the MATLAB function block, and the editor window appears, allowing us to write the code using the MATLAB language for this block. We write a function that calculates the z, y and z coordinates of the end effector as output signals. The function name is forward kinematics. The input variables are the robot's joint variables. The calculation itself will use the specific size values of the robot and the homogeneous transformation matrices determined by the Denavit-Hartenberg method, which we defined at the beginning of the lecture. To write the code for the forward kinematics function in the MATLAB function block, Let's review the assigned coordinate frames and the homogeneous transformation matrices determined by the Denavit-Hartenberg method. We calculate the homogeneous transformation matrix TAT describes the orientation and position of the end effector relative to coordinate frame 0 using the formula shown on the slide. From this matrix, we can then determine the x, y, and z coordinates of the end effector. The detailed code for the forward kinematics function, which calculates the forward kinematics, is implemented as shown in the video image. Once the function code is complete, we connect the block's input signal to the same desired joint input signals of the robot for testing. For the output, we also use display blocks. At this point, we have successfully completed the entire model. We run the simulation to verify the results. The simulation results show that the x, y, and z coordinates of the end effector, as measured by the sensor in the multibody model, are exactly the same as the results calculated by the forward kinematics function using the matrices. Let's take one final look inside the multibody model. With this, we have successfully completed the simulation and verified the correctness of the method. Thank you for your attention. You can try doing it yourself to better understand the process in detail.